Welcome back, everyone. So in this part of our Chapter 4 series, we're going to be taking a look at solutes and how they can be classified as either strong or weak or non-electrolytes. Strong, weak, or non-electrolytes. Now, all right, we can classify solutes as strong, weak, or non-electrolytes ultimately based on how many ions they produce in an aqueous solution. And so it says right here that solutes can be classified as strong, weak, or non-electrolytes based on the extent to which they produce ions in an aqueous solution. So when we dissolve solutes in water, some solutes are going to produce a lot of ions. Some are going to produce few ions, and some are going to produce no ions at all. And this is ultimately the method by which we classify those solutes as either strong, weak, or non-electrolytes. So let's start from the top here by taking a look at our strong electrolytes. So strong electrolytes are, maybe you're not surprised here, are the ones that dissociate 100% into separated ions when dissolved in water. And this means that the resulting solution contains a large quantity of just ions floating around, evenly dispersed among the water molecules. Okay, well, what sorts of substances could we classify as strong electrolytes? Well, it turns out there are three major categories of strong electrolytes. And the first category of strong electrolytes are soluble ionic compounds. Well, how do we know if an ionic compound is soluble or not? And I did not spell ionic right here. Soluble ionic, there we go, compounds. Well, we know an ionic compound is soluble or insoluble by checking our solubility rules. Check solubility chart. And if we were checking a solubility chart, we would find that many different ionic compounds are soluble. So for example, we might have things like, say, potassium iodide is a good example of a soluble ionic compound. Or perhaps something like aluminum sulfate is a good example of a soluble ionic compound. Or perhaps even ammonium chromate is a good example of a soluble ionic compound. Many examples of soluble ionic compounds, and I'll put etc. Just check your solubility chart. Now, the second important category of strong electrolytes are what are known as strong acids. Strong acids. So what is a strong acid? Well, it's a strong electrolyte. It separates 100% into ions in solution. Now, it turns out of all the acids out there, there are only 6 acids that we classify as strong acids. And as it turns out, you are going to have to memorize the 6 strong acids. So what are the 6 strong acids? Well, hydrochloric acid, HCl, is one of our strong acids. Hydrobromic acid, HBr, one of our strong acids. And hydroiodic acid, HI aqueous. These are sometimes called the strong mineral acids. In addition to these 3, we also have HNO3, which is nitric acid. The 5th acid in the series is HClO4, or perchloric acid. And the 6th acid in the series is H2SO4, which of course is sulfuric acid. Please write down the names if you're still not good with naming these acids. That's an L, not an I. Perchloric acid over here. So you've got to memorize these 6 acids. The strong acids are all strong electrolytes. Now, the third category of substances that are considered strong electrolytes are strong bases. Now, we haven't talked about bases before. Well, what is a base? A base is a metal hydroxide. Now, any metal with hydroxide makes a base. Aluminum with hydroxide, aluminum hydroxide is a base. Magnesium with hydroxide is a base. Okay, but what makes a base a strong base is that the metal hydroxides have to be soluble. So a metal hydroxide that is soluble is a strong base. So strong bases equal soluble metal hydroxides. Now, once again, how would we know which metals coupled with hydroxide make a soluble metal hydroxide? By the way, all right, we could write this as MOH. Well, it turns out the metals that make hydroxides soluble, if we looked at our solubility chart, include all of the group 1A metals. So the metal would have to be from group 1A. So our group 1A metals include lithium, sodium, potassium, rubidium, cesium. And as it turns out, a couple of metals from group 2A also produce soluble metal hydroxides, and they are the barium cation and the strontium cation. Okay, so any metal from group 1A combined with hydroxide is a strong base. All right, barium combined with hydroxide is a strong base, and strontium combined with hydroxide is a strong base. And all of these substances here count as strong electrolytes. Well, let's scroll down a little bit so that I can illustrate what I mean when I say that these substances are strong bases. Okay? Or strong acids, or soluble ionic compounds, all strong electrolytes. Okay. Well, let's suppose we put a soluble ionic compound in water. Let's suppose, here, let's get a pen here, that I put some potassium iodide in water, which is a soluble ionic compound. Well, what would we expect to happen? Well, it's soluble. It's going to dissolve. But we know that these ionic compounds that are soluble, all right, split apart how much? 100% into ions. So when we take a look at the solution, there is no whole Ki's in the solution. Instead, we have a bunch of K pluses floating around in solution amongst iodides, also floating around in solution. Let's put the same number. In other words, we have a solution filled with ions, and only ions in the resulting solution. Well, the same is true if we have a strong acid. Let's take a strong acid such as HCl. Well, again, if we were to look under, a microscope that could see down to the molecular level at a solution of a strong acid, well, what would we see? Well, we wouldn't see any HCl in there, but what we would see are separated hydrogen cations and chloride anions floating around in the solution. So chlorides floating around amongst the hydrogen cations, nothing but ions, separated cations and anions in the solution. And last but not least, the same is true for a strong base. Let's take a strong base like sodium hydroxide, which dissolves readily in water, again to produce what? A solution of nothing but ions. Sodium ions floating around with hydroxide ions. Let's put in those hydroxide ions. A separated soup of ions is what we have in solution for our strong electrolytes. So let's note down here that the solutions of strong electrons contain only ions. And these ions will be present in large quantities. Lots and lots and lots of ions in these solutions. Now, it turns out separated ions in solutions can move about freely. And because the solutions have these freely moving charged ions, these solutions are very good at conducting electricity. So these are good conductors of electricity. And we often call the solutions of strong electrolytes, which are filled with nothing but ions, we call these electrolytic solutions. Electrolytic solutions is what they're called. Okay, So now we've taken a look at solutions of strong electrolytes. Well, let's now take a look at weak electrolytes on the next page. Now, in contrast to strong electrolytes, let's just go back here, where we said strong electrolytes dissociate 100% into separated ions. Well, weak electrolytes do not. So let's get a new pen color here. I don't know. Let's go with green. Green is pretty. So now we're taking a look at weak electrolytes. And how much do they dissociate? Only slightly. They slightly dissociate into separated ions when dissolved in water. What do I mean by slight? Well, certainly not 100%. All right. Typically, it's not unusual for weak electrolytes to dissociate less than 20%. Some weak electrolytes will even dissociate less than 1%, so very little dissociation into separated ions when dissolved in water. So what does this mean? It means that most of a weak electrolyte remains, oh, that's a terrible underlining job I'm doing there. I think I do better with the highlighter. So most of a weak electrolyte remains undissociated, and that means that the resulting solution contains just a small quantity of ions dispersed among the water molecules. Okay, well, let's take a look at examples of substances that behave as weak electrolytes in water. Well, the first category of weak electrolytes are insoluble ionic compounds. Insoluble ionic compounds. Now, once again, to know if an ionic compound is soluble or insoluble, what do? You check your solubility rules. Check solubility chart, which is provided for you as a separate handout. So if we were to take a look at that handout, we might identify some insoluble ionic compounds, such as, say, oh, I don't know, silver iodide, or perhaps aluminum sulfide, or perhaps zinc carbonate. These are all good examples of insoluble ionic compounds, and of course there are many, many, many more, and they are classified as weak electrolytes. Okay. The second important category of weak electrolytes are weak acids. So strong acids were strong electrolytes. Weak acids are weak electrolytes. We saw earlier that there are only 6 strong acids and you have to memorize them. Well, very simply, if it's not one of the 6 strong acids, it's got to be a weak acid. So let's write here, if not one of the 6 strong acids, it is considered to be weak. Okay. Well, it means there's probably going to be a lot more weak acids, correct, than strong acids. Let's just put a couple of examples of weak acids down here. So, for example, HF, hydrofluoric acid, is considered a weak acid. Or perhaps HC2H3O2, that of course is acetic acid, is a weak acid. Or perhaps H3PO4, which is phosphoric acid, also considered a weak acid. And again, many more, etc. As long as it's not one of the 6 strongs, it is a weak acid. Now, the third category of weak electrolytes are weak bases. Now, it turns out we're not going to talk much about weak bases because we're not quite at the point in the curriculum for you to really understand how weak bases act as weak electrolytes. A good example of a weak base that acts as a weak electrolyte is ammonia, NH3. But this category we're not going to pay attention to right now. All right, this is going to be covered later in Chem 12, actually. So weak bases are weak electrolytes. We're just not going to be worrying about this category of weak electrolytes at this point of time in Chem 11. So that means we're really going to be focusing on the first 2 categories, insoluble ionic compounds and weak acids. Okay, well, let's see how these substances behave a bit differently when we put them in water. So scrolling down, Scrolling down, scrolling down, scrolling down. Well, let's suppose we have an insoluble ionic compound, such as silver iodide. Okay. Now, if we put some silver iodide in water, all right, well, it's insoluble. You don't expect it to dissolve, which means all the ions remain bonded together within the crystal lattice. So we expect to have, some silver ions with some iodide ions with some silver ions. Okay. But it turns out that even in insoluble ionic compounds, a very small amount will actually dissolve in water, usually an amount too small for us to even see by eye. And so even, all right, an insoluble compound like silver iodide will dissolve to a very slight extent, like so. So maybe just 2 ions from that crystal lattice will pop off and be pulled away by water molecules. Not very many get pulled away. Why? Because it's insoluble. Now, what does this mean? It means, oops, let's get a highlighter here. It means that, we're using green right now. It means that most of the ionic compound remains in solid form, and that most of the ions remain together in the original crystal lattice, which is why, we typically write this as solid because most of it remains in solid form. So let's just get a pen over here and note that most ions over here remain undissociated in the crystal, in the solid crystal. So most ions remain undissociated in the solid crystal, is what we have here. So this is a very different picture than what I drew for the potassium iodide, which was a soluble ionic compound and a strong electrolyte. There was no solid hanging around, and all we had in that solution were ions, a solution of pure ions. Now, let's take a look at an example of a weak acid. So let's take a weak acid such as, say, hydrofluoric acid. Okay. Now, hydrofluoric acid, all acids are in the aqueous state. But a weak acid in solution is going to look very different than a strong acid in solution. Why is that? Well, it's because most of the HF remains whole and undissociated. Most of the HF molecules do not break apart into ions. Only a very small number of those HF ions break apart. So let's just put one F minus and one H plus. So once again, what we see here is the HFs stay mostly as undissociated molecules. Okay? And only a very few split apart into ions in the solution. So let's also make a note of that over here. So, all right, most remains as, in this case, undissociated acid molecules. Is what we end up having here in the solution. Now, ultimately, what makes these weak electrolytes is the tiny number of ions they're producing in solution. So it doesn't matter whether I'm looking over at this solution or this solution. All right, we don't see very many ions being produced. So there are few ions formed in solution. And this is what makes these substances weak electrolytes, because they produce so few ions in solution. And you might imagine that having so few ions floating around in solution is not going to make these solutions very good conductors. In fact, these types of solutions are poor conductors of electricity. Okay, so very different picture between our strong electrolytes in solution and our weak electrolytes in solution. Well, that takes us to the third category of electrolytes, which are our non-electrolytes. And yes, as you might imagine, our non-electrolytes are ultimately substances that do not produce any ions at all in aqueous solution. So over here, we're now dealing with non-electrolytes, and what happens? They do not dissociate into any ions at all when dissolved in water. And this means that when a non-electrolyte dissolves, how does it remain? It remains as undissociated molecules, and that's all you end up with in your solution. And well, it turns out that the only category of substances that count as non-electrolytes, so just one category only, are molecular covalent substances. So molecular covalent solutes are good examples of non-electrolytes. So we saw from an earlier lecture, C6H12O6 would be a good example of a molecular covalent solute that, all right, would dissolve in water but stay as whole molecules. Or water itself is a molecular covalent substance, or carbon dioxide, or perhaps alcohols such as ethanol, C2H5OH. Okay, when you put these substances in water, well, what happens? They stay whole. So if I have a solution of C6H12O6, which is a non-electrolyte, whoops, this should not be in the solid state, that should be in the aqueous state because after all it does dissolve. What would you have in solution? Well, you wouldn't have any ions at all in solution. What would you have in the solution? You would have whole C6H12O6 molecules, all floating around, interspersed with all the water molecules. C6H12O6, C6H12O6. So all of these molecules remain intact molecules. And do we have any ions? No, we have no ions in these solutions. No ions. And of course, these solutions, therefore, are not going to be good conductors at all. So once again, let's note that these are poor conductors. Solutions are poor conductors of electricity. Okay, so now we know the difference between solutes that behave as strong, weak, and non-electrolytes. And again, it's all about how many ions they're producing in water, to the extent to which they produce ions in water when they are dissolved in water. Okay, that's it for now. I will be talking to you very shortly again, I hope, but tune in for your next lecture where we're going to start looking at solutions quantitatively, and that of course means concentration. Bye now.